Well, I guess we'll sort of get started in the way we do, but before we actually go on to the technical stuff, we'll just find out a bit about your background in CCS, Colin. So I met you. When would it be? Late 80s.
When you were a PhD student at Imperial.
A PhD student at Imperial. So maybe not so late 80s even, but
yeah.
So at that point, you weren't doing CCS, were you? You were doing coal hydrogenation. Okay,
so basically, journey into adsorbents is coming an academic. 1987, knew a bit about catalysis from my coal industry days, so built up quite a big effort on catalysis, and catalysis naturally leads into adsorbents. So,
but how do you get into coal, into the coal industry, Colin? Let's just go back a little bit further.
If everybody's listening, this is a very amusing story. Cast your minds back to 1974, which was the second miners' strike.
Yes.
As things were in the 1970s, wasn't really in much of a hurry to get a job.
So three-day week, right?
Yeah, so it's a 3-day week. And had a chat with my dad, and he says, "Oh yeah, didn't you apply to the coal research establishment?" I said, "Oh yeah, Dad, that's right. Never heard anything." And he said, "Leave it to me." Within a week, I got an invite down to Cheltenham, and it was the most easiest interview you could imagine. And when I started in September, I found out they thought my father was a leading militant in the Durham branch of the National Union of Mine Workers. So I've really got to thank my father for the career path I've gone down. But clearly, 1985, the Scargill miners' strike, the writing was on the wall. So hence I moved into academia 87, and here we are 33 years later.
And were you at Nottingham all the time? No, you weren't, were you?
No, it's north of the border, so Strathclyde, 13 years to 2000, moved to Nottingham. And the move to Nottingham was, the reason I did it was John Patrick was at Loughborough. I mean, John actually lives in Nottingham anyhow. So at the time, it just seemed to be a good thing to combine our efforts into one, as it were.
Yeah, and how have you found moving down south then? After, I suppose it's sort of a lot further north than Cheltenham, anyway.
Yeah, so it's further north than Cheltenham, but still quite a way south in relation to my native northeast.
Yeah. So you're doing catalysis. I mean, what sort of things were you doing catalysis on?
Oh, I mean, that was all coal liquefaction stuff. Which I then, at the time in the 1990s, just migrated that into traditional petroleum processing, hydrocracking, fluid, catalytic cracking, etc. So it was really the grounding in catalysis that made the jump into adsorbents possible. So first paper on CO2 adsorbents was 2004.
2004, okay. Yeah, and
so here we are 16 years later.
Yeah, I was going to say, how much do you think things have moved since then?
Well, that's exactly what I'm going to talk about.
Okay. And just going back to coal, I mean, we're still seeing a lot of coal burnt in the world. I mean, what's your thought on the likely long-term fate of coal? I mean, China's said 2060 for net zero for them. I mean,
well, I mean, clearly what happens in China, because they account for over 50% of global coal consumption, but the rate of change of things in China, you can imagine there's going to be quite a lot of redundant, fairly modern power plant.
Yeah.
I mean, China's interesting because we can't really make the transition UK has, Europe has, which is going down the natural gas route essentially as a transition route to wean you off carbon completely.
Yeah, yeah. No, it's going to be interesting how they come up. And then Nottingham's got quite a bit to do with China. How's that going at the moment?
Well, because, yeah, I mean, we've seen plenty of Chinese students turning up, but clearly on research front, direct contact is limited. But yeah, I mean, we're still active, and as I'm talking about today, quite heavily involved in Korea as well.
Okay. All right. Well, so that's a bit of background. Just question I should ask: what was your first degree, Colin?
First degree, 1974, chemistry from Sheffield. I did a PhD working part-time, so essentially had the best of both worlds. Got my PhD from Leeds, 1981.
Yeah, so you stayed. So I will ask you a question then. I mean, presumably Sheffield's changed out of all recognitions in 1974, right?
Yes, I mean, some things haven't changed, like the roundabout in front of the chemistry building, which I spent many happy hour looking out of the window doing final year undergraduate research project. Of course, the Arts Tower as well. I think pretty much looks the same, but Students' Union, where clearly watched some great rock concerts. That's been demolished and rebuilt.
Yeah. And did you get out into the Peak District much when you were there, or you?
Yes, but I mean, I played quite a lot of football, so I took up a bit of the time. But Peak District was really reliant on friends who had cars, and we all know about the lock-ins in Derbyshire pubs to the early hours in the morning.
Very good. Good student life. Okay, sorry, catalysis and then getting into and solids capture, Colin. Thank you for the background.
Right, so are you still there, John?
Yeah, I'm still there. I'm going to stop my video just to avoid distraction.
So we kick off, and if you can tell me to shut up in, I don't know, 30 minutes time to allow plenty of time for questions. Okay, so what I'm going to take you through today is really solid adsorbents as a next generation technology for CO2 capture. And really what I'm going to be concentrating on are the challenges and pitfalls regarding scale up. As you can see from the introductory pictures, the theme is very much on scale up. On the left-hand side, we're looking at the largest demonstration globally, which is at Hardong Power Station in Korea. And this is equivalent to 10 megawatts. On a much smaller scale is our continuous rig for testing adsorbents at Nottingham, which roughly operates on 5 to 20 kilograms. And I'm giving this presentation from my office, and on the right hand side is the building I'm sitting in. So the work in part has been funded by UKCCS Research Centre, and of late we've had a very fruitful relationship with the Korean Institute of Energy, and also we've received capital funding from Energy Research Accelerator in Innovate UK. So in terms of introduction, I'm sure you've all seen this slide many times, but obviously both of us are doing research. This is the direction of travel we hope we'll go on in terms of new materials, second generation technologies. We'll scale up, and and we'll do demonstration. We'll learn from the demonstration, and the cost will come down. More demonstrations, the cost will come down further. I think most of these slides were based on experience for flue gas desulfurization, which is an exothermic process, and there is a lot to be gained for learning. My view is the steepness of the curves presented, obviously schematically here, are far too steep because of the inherent energy barriers that you have in CO2 capture technologies. So just to focus on solid adsorbents, I just thought I'd show you a slide from 2003, giving you the range of materials which were investigated: zeolites, activated carbons, hydrocalcites, zirconias. I've used a bit of poetic license here. I've added metal organic frameworks, and if you're wondering what a COF is, it's a covalent organic framework or a porous organic polymer. And the interesting thing, all these materials, 17 years later, not one of these has reached a small demonstration scale. So what I'll do is I'll just tell you something on clearly the driving force for wanting to investigate solid adsorbents as any other second, third generation technology in terms of reduced energy penalties. The focus is going to be very much on silica polyethylene imine as a strongly basic system and a weaker CO2 adsorbing system, activated carbons. The reason is, at the moment, these are the ones which are the most economically feasible. But really what I'm going to focus on is all the issues that really you need to consider on the journey for scale up in terms of stability, moisture co-adsorption, which I'll bang on about quite a bit as a under investigated factor. And I think as well with amines, what is critical here is what is the cost of the replacing your solid adsorbent per ton of CO2 captured. So I'm going to take you through the journey we've been on, scaling up from 2, 10 to 100 kilograms scale. And as already mentioned, a lot of this has been done in conjunction with Korean Institute of Energy Research, who sort of built and designed the plant at Hardong Power Station. I'll show this as a slide prepared by Kia rather than myself, because I would be far too modest to put the University of Nottingham on this slide. But really, the take-home message is, if we look down the bottom row of the entry for Kia, is essentially what's happened at a 10 megawatt scale. That plant is still operating. But apart from that, the only other plants that have reached any sort of reasonable scale are ADA, ES, second row down, operated a 1 megawatt equivalent facility, albeit for just a short length of time. And also in the USA, RTI have got to a stage somewhere around about 1 megawatt. But with both these demonstrations, you look in the literature, apart from summary presentations, it's very, very difficult getting real actual performance data. So clearly, on the journey from getting published in the highest impact journal as possible for the new material you've just discovered, which displays a high adsorption capacity for CO2, I've just listed the obvious factors that might derail you on the journey in terms of scale up as you move to pilot and demonstration plant, particularly physical properties, stability, moisture co-adsorption. And as I said, I'm going to focus on the work we've done on silica-PEI and activated carbons, really to take you through the journey so you can see how some of these factors play out. So let me take you back 11 years to 2009. And essentially, this is what we published. And this is quite a useful slide to show the difference between a strongly basic system, in other words, silica polyethylene imine, and activated carbons, which absorb CO2 much less strongly. So you can see from the red line at the top, silica-PEI, you have to go to temperatures way above 100 degrees to dissolve the CO2. Activated carbons, you can see, and this is in 15% CO2, have similar absorption capacities at low temperature, but the CO2 is rapidly dissolved, and a bit over 100 degrees, you achieve complete desorption. So really, I'm going to say something briefly how things have developed over the past 11 years. But before I do that, what is very important in everything I'm going to say is the regeneration energy. And in the interest of time, I'll just present this in a qualitative sense, that the three principal terms you've got is latent heat of CO2 adsorption. You obviously need to overcome for desorption. There's a sensible heat for heating everything up to your regeneration temperature. And the thing that nobody bothers to investigate, which I'll show is crucially important, is latent heat for steam, for any moisture that's co-absorbed. So clearly, we want things with low sensible heat, and this is where adsorbents score heavily over amine solutions. Ideally, we want to minimize the heat of adsorption, so the activated carbons have much lower heat of enthalpy of adsorption than silica-PEI, and clearly we want to minimize temperature difference between adsorption, desorption, and, as I've said, moisture co-adsorption. So we've looked into this in some detail, and we published a comparison with what is taken to be an advanced MEA system, where you are getting down to round about 3 gigajoules per ton of CO2. Taking a very, very conservative approach, we estimated that you should get down to the order of 2.5 gigajoules per ton with silica-PEI. Key parameters in all of this are the working capacity of the adsorbent, and this is based on a very conservative working capacity of 5 weight%. You saw on the previous slide, but the equilibrium capacity is around about 10%. And the one thing that really kills you is moisture co-adsorption. It turns out on silica polyethylene imine, we only absorb 1 or 2% moisture, but each percent moisture is costing you 0.25 gigajoules per ton. How you can make use of the surplus energy is important, but again, just to gloss over all of this, we've assumed very, very conservative parameters for this. So we did a similar paper extending this to what effect would it have on an actual power plant, and again, this is compared with a advanced MEA, 2 cases for supercritical pulverized coal, natural gas combined cycle, and you can see how this works out in terms of efficiency points. And again, just to re-emphasize, we're very conservative figure of 5%. If we can get anything over 5%, the picture improves markedly. So can we do anything better than we did 11 years ago? The answer is yes. We can make silicas with much better properties, and basically because polyethylene imine is a polymer, what you want is a silica with plenty of large mesoporous volume, and we can make silicas by this route, but I'm not going to go through it, but you can see there's many steps involved, and what we're starting off with is rather than just dissolving silica in sodium hydroxide, we're using an organic precursor. We have many organic reagents in the preparation. So to cut the long story short, this will increase the cost of your silica by a factor of 10 or more. So is this worth doing? And the bottom line is the increased pore volume we're obtaining. So we can typically increase pore volume by 50%, and this has a knock-on effect. We can absorb more polyethylene imine, and this gives us correspondingly higher uptake. So yeah, we can do better, but it does come at a price. So to move briefly onto testing, we started working on a 2 kilogram scale, rather simple fluidized bed here, which was just used in successive adsorption, desorption cycles. And just to point something out, for fluidized beds, it's very difficult getting the right particle dimensions to give you a reasonably small minimum fluidization velocity, so you can achieve a reasonable residence time and getting the right particle size range to do this. And I just throw in a couple of carbon materials. We have a problem with carbons, they're very weak, and you do have a trade-off. You have to make fairly large particles to get the strength, but to do that, you've got high fluidization velocities, which minimizes your contact time. So once you start considering fluidized bed systems for carbons, you do run up against some serious practical issues. So silica-PEI, and this is basically our 2009 preparation here. So life worked out very well, went through over 60 cycles, so this corresponds to 2-3 weeks continuous operation. Operating capacity was maintained, and we learned very, very quickly, all you have to do is keep some moisture in the system. So moisture prevents polyethylene oxidizing during adsorption, and during desorption, if you carry it out dry, CO2 and amine groups react to give you urea, and we found out early on you can avoid this reaction by having moisture present. If you don't have moisture present, you quickly kill your adsorbent in terms of oxidation urea formation, as you can see by the reduction in adsorption capacity in this particular slide. So really, I think due to the success of that initial exercise, Kia came to us and asked us, like, could you scale up the Sorbent? And we said yes, taking a rather deep breath at the time. And what we thought we'd better do is look at particularly the PEI composition, and you do have many variables. I'm just highlighting here molecular mass, because PEI comes in a very convenient form. It's normally transported 50% solution in water, and this is great. All you have to do is contact it with your silica, dry the mixture, then you've got your final adsorbent. You look in the literature, vast majority of people use organic solvents for contacting the PEI with silica. There's no need to. Water is perfectly fine. And in terms of molecular weight, clearly you've got potentially greater stability, but viscosity of your solution increases, and we rapidly came to the conclusion that a moderate molecular weight represented the best compromise. So we could do this very reproducibly, and we got exactly the same performance as we did on a lab scale way back in 2008, 2009, equilibrium capacities bit over 10%. So this is how we literally made 100 kilogram. Here we are mixing the silica-PEI together. We didn't dry it ourselves. We went off to a double cone vacuum dryer to do that before it was shipped to Korea. So once it got to, first of all, just to prove it was extremely reproducible, these were separate batches of the silica-PEI, and you can see performance is constant right across the different batches prepared. So once it got to Korea, this is what's happened. The first system is 2 bubbling fluidized beds, so for equivalent. So we've got one for adsorption, one for desorption. So adsorption was roughly 70 degrees, desorption was 130 degrees. We looked at a lot of variables, but to cut a long story short, how you operate the fluidized bed, it's essentially a compromise between the amount of CO2 removed and your dynamic adsorption capacity. So you can see we were well over the 5% minimum, which we set us, and CO2 capture rates around about 80%. We were slightly concerned because moisture wasn't always present at every stage in this particular rig, but we had a big sigh of relief afterwards. If you can see the pictures on the left-hand side, the little capsules, the silica-PEI is still white. If it's still white, there's no color. There's very little degradation. This work did confirm that the amount of water taken up is relatively small, so the contribution to the regeneration is certainly no more than 0.5 gigajoule per ton of CO2. So that was done chronologically. That was done before we prepared the 100 kilogram batch. The 100 kilogram batch was a larger rig. The difference was, if you can see the schematic in the bottom right hand side, we had a circulating fluidized bed riser for adsorption, desorbers before, and a lock-upper seal, the blue vessel just to cool everything down. Again, the results were very, very similar. So the compromise situation is getting high dynamic adsorption capacity. So you can see around about 7.5%, way below the 5%, way above the 5% target we set ourselves, and CO2 removal efficiencies around about 90%. So this tells us, in reality, we can potentially do a lot better than what we said we would do in the modeling studies we published in 2016 and 17. So that's really the picture for silica-PEI. I'll just say something. Sorry, just one thing. To reiterate, moisture wasn't present at every stage in the rig. So when we did analyze the adsorbents after 108 hours operation, we did see some loss of activity, but this is fine. We know the reason why it happened, so we can make sure it doesn't happen again in the future. So let me briefly switch to carbons, and we sort of got very interested in carbon beads because they were strong. They could be made from resin precursors quite easily. And really, from what we published in 2009, it was evident to get the benefit of high CO2 absorption capacities, you have to activate with potassium hydroxide. So if you look at the graph on the top right-hand corner, you can see roughly the CO2 absorption capacity has doubled because we've treated, activated the carbon in CO2. This is under, again, 50% CO2 to simulate pulverized fuel combustion of coal. So this was all well and good, and what is happening is the potassium gets intercalated in the carbon. The CO2 is bound slightly more strongly, but roughly enthalpies of adsorption are only increasing roughly from 25 to 35 to 40 kilojoules per mole, and this compares with around about 90 kilojoules per mole you've got with strong basic systems such as polyethylene imine. So anybody who's followed the literature recently will realize there's a whole plethora of papers on taking potentially various waste materials, putting them through some form of KOH activation, and getting very high CO2 absorption capacities. We are no exception. We've joined in the fun, and I just want to take you through two precursors. Chen Gong Sun, I think, talked about these in much greater detail, but just taking rice husks, KOH treatment, we could generate materials that have very small micropores with potassium intercalated, and we were obtaining high CO2 uptakes over 2 millimoles per gram at 20-25 degrees C. So the key is, as well as intercalating potassium, is generating small micropores, and this theme has really continued in work that's just been published this year on using essentially a form of polyurethane, polyisocyanurate resin form, and all you have to do is oxidize your foam, compress it to increase the density, then KOH activate. And with this material, it's a combination of small ultra-micropores, around about 0.4 nanometer, potassium incalated, with nitrogen functionalities playing a bit of a role. But the headline figure is we can get up to over 2 millimoles per gram at 40 degrees. So that's obviously much higher than the 25 degrees, which featured on the previous slides. So all this sounds wonderful, and clearly with the proviso for activated carbons, you really have to think in terms of a moving bed rather than the fluidised-bed system for scale up. But before we move on to scale up, what can really knock you for 6 for activated carbons is moisture absorption. And this just compares the rate of moisture uptake at different relative humidities at ambient temperature. And again, just let me remind you the bottom line, 1% moisture, 0.5 millimole is adding 0.25 gigajoules per ton onto your regeneration energy. And if you just look at the black line, which is our polyisocyanurate resin, potassium activated carbon, you can see that is giving the highest moisture uptake. So it turns out that across the carbons we're looking at in these slides, if you look at the CO2 moisture uptake, there is some variation, but much less. But I just want to point out, taking something that is actually commercially available at the moment, which is coconut shell activated carbon, if you treat that with KOH, you get very low moisture uptakes, and you know, roughly 10 minutes is a sort of reasonable time you'd expect your material to spend absorbing CO2. And the coconut shell, you can see after the order of 10 minutes, even at relative high humidity, you know, we're still in the region of roughly 2 millimoles. But clearly, this is for one thing that nobody ever publishes in the literature and can kill you stone dead in terms of regeneration energy for carbons. So my other cautionary note is on scale up, because clearly buoyed by the success of what we did at the lab scale, we thought let's try scaling up. And the one thing I need to say is today commercially throughout the world, nobody produces KOH activated carbons at large scale, and clearly the reason is obvious, is KOH at 800 degrees is highly corrosive. So we did persuade our colleagues at CPL to take some carbon beads, put these through the rotary kiln, and as you can see, we are losing some of the initial performance as we go to larger temperatures. It gets very difficult to reproduce what you did on a lab at a small scale, and the story is very similar for the polyisocyanurate resin foam, where we do low temperature oxidation, and trying to do a low temperature oxidation on a solid gives you huge problems trying to control the temperature. And just if you look at these pictures, you can see the material we end up with is extremely heterogeneous. It's the light material we want, but it's very difficult to stop the exothermic oxidation getting out of control and giving you some of the darker material. And you can see that as you go to higher and higher temperature, you lose some material. And when we compare lab preparations with what we actually prepared on a larger scale at CPL, you can start to see we are losing activity, which can be ascribed in part to this over-oxidation and also in part to some of the activity that's lost with KOH. So I'm nearly at the end now. John, how many minutes is that? Oh, sorry, Chairman is offline, but according to my watch, a bit over 25 minutes. So,
I mean, you know, we've got time, Colin. Just
yeah, so clearly, in terms of the overall, putting this into context, this slide is very important. And what I'd really welcome in the discussion is, because clearly, whatever technology you've got, you want to try and minimize your material replacement cost. And I put the numbers for other capture technologies in brackets because these are what I've been quoted rather than what I've read in the literature. But I've heard from more than one source that for MEA scrubbing, you're looking at anything up to £15. High temperature calcium looping, because it's clearly relative cheap material you're using, calcium oxide, calcium carbonate, the cost is much lower. So what I thought I would do is I would set myself a limit of £10 per tonne of CO2 captured. And I thought I'd again take very conservative operating parameters. Adsorbent going around, taking 40 minutes to go around the loop, that's adsorption, desorption cycle. And what we think is a very conservative working capacity of 5% weight percent CO2. So if you do the arithmetic on that, you can work out that in a year, 1 tonne of adsorbent will capture 1,000 tonnes of CO2. So we're dealing in nice round figures. We all know that MEA is relatively cheap, somewhere around about £1,000 per tonne. The best estimate I can give you for silica-PEI at the minute is pushing down to 10,000 tons, but as you know, as you produce things in greater and greater in bulk, the cost will come down. But if we take these costs of 10,000 pounds per tonne, £10,000 per tonne keeps us within this £10 limit. But the big but is your adsorbent has to last for 1 year. So, sorry, jumped ahead. So I think this serves as a sort of useful benchmark for comparing all solid adsorbents. Activated carbons are cheaper, but as I just highlighted, issues over production, they're not that suited to fluidised bed operations. So you happen to be looking at moving beds. And yeah, if you look at the cost of a moth at the minute, probably £100,000 per tonne. So unless the cost comes down by an order of magnitude, also with moths, moisture co-adsorption is very rarely addressed. Physical durability, what is the impact of particle size? Just to finish on, we know how to improve PEI stability markedly over what I've shown you for the trials we did in Korea, and this is very much the future direction of our work. Unfortunately, I can't talk about this today due to IP, but let me conclude, and because of my years, I think most of you know, but I am partially retired, and one or two people have indicated that I have come somewhat more grumpy over the last 2 to 3 years. But I think if you go back to the original slide of 2003, there's been considerable scale-up challenges, which I think have slowed down the pace of development. I've not talked about air capture today, but in terms of material challenges, it's somewhat Asian PEI, and we're published on this, is ideal for low temperature air capture. As I've indicated, there is scope for cost reduction, and really the simple economic analysis is if your material costs £10,000 per tonne, then basically it has to last roughly for a year. Activated carbons do have limitations, potentially with respect to moisture co-adsorption, particle size, and clearly weaker CO2 absorption means you're only looking at cement and coal. There's no way you can use activated carbons on gas. And even though I've got to hold my hand up and say, you know, we've been as guilty as everybody else in putting out loads of papers on new adsorbent materials and just focusing on CO2 uptake. But the grumpy old man in me now says papers should not be published unless they address one or more of the following factors in some detail. Those factors being moisture co-adsorption, particle size, physical and chemical durability, and yes, how easy it is to scale up the material. So I'll rest my case there, and finally just to acknowledge the sponsors, because I've summarized over 10 years of work in half an hour in terms of research councils, EU and international collaboration with Korean Institute of Energy Research. And I couldn't introduce all my core workers, but across Korea, Shanghai Advanced Research Institute in China, and University of Nottingham. Here's a list of all our collaborators. Thank you.
Thanks very much, Colin. That's very good. Yeah, I wouldn't say you've got more grumpy as you've got older. I think you've
Oh,
mellowed.
well, I think you can only see me now. I think if you saw me 4 hours a day,
Okay.
you might change your opinion.
Very good. Very good. Well, anyway, I'll just ask a sort of a bit of a question. I mean, you say that these questions should be asked, and you sort of said it in your presentation, but why do you think they haven't been more at the fore as things have developed?
Well, I think you just
can I just I think
it's a publication culture, John.
Well, but I mean, who's refereeing the publications then?
Well, I mean, this is it, and this is really my recommendation. There needs to be, shall we say, an international panel formed across all the journals where people publish it and say, from now on, we've had thousands and thousands of papers on new materials, but I think we've reached a stage, unless you start addressing the factors that really matter, then, you know, sorry, will not publish.
And, I mean,
that's about as grumpy as I'm going to be, I guess.
Yeah. Do you think you might get that with more industry involvement? I mean, have you?
Oh yeah, I mean, it's certainly much. I mean, that's been our focus pretty much since the early days. But we still playing around with materials, and if you come up with something that's got a high CO2 absorption capacity, then yeah, you're going to get it published.
No, but what I'm saying is, in terms of sort of these practical issues, do you think if there was more industry refereeing?
Yes, certainly. Industry refereeing would say, yeah, why don't you go and think of this? Because if you don't, there's no way you're going to be able to stand up.
Yeah. So presumably there isn't really that much practical industry interest in deployment. Otherwise, they'd be.
Well, I think there is. Yes. Yeah, but is sorry, I can't really say too much about it at the moment. But clearly, for silica and PEI, we've got clearly silica and PEI producers on board. We do have major industries on board.
But generally,
against scrubbing, oxy-fuel combustion, and the close times we've got with Korea, when we do have the funding to make 100 tons, then we can't go to the 10 megawatt equivalent stage.
But in the publication field, it's generally in the field, it seems like industry is a bit lacking. I mean, it's just a comment on where you say.
I mean, economic assessment papers, they were co-authored with PQ Silicas and did do some Babcock who were interested in the technology at the time.
Okay. I mean, just to comment on.
I guess, sorry, I will learn how to use the chat control. I'll see all the questions.
Yeah. I'm just using the chair's privilege, but some more questions come in. But what I was going, one of the comment, I mean, just on MEA, $1,000 a ton and pounds a ton is about right. But I don't think you get up to $15. But you do get it. You certainly have got up to $15 on Boundary Dam for a proprietary solvent.
Oh yeah, I mean that's why I put in italics. I've heard it from a number of sources, but it's not the thing you're going to find published in the open literature.
If you know where to look, you might do.
Yeah, well, anybody who can find that information actually state it in a paper which is based on real operating experience, please let me know.
Yeah. Okay. All right. That's a question.
Sorry. So, yeah. Sorry. I can see the questions. So
let's see if the people want to ask the questions, though, if you don't mind, Colin. So Salman Masoodi, do you want to come on and ask a question?
Oh, hi, Colin. Thank you very much for the presentation. Very informative, really. So I was wondering whether I could have some information, some insight into the composition of the flue gas that you use with the activated carbon.
Okay, so everything we've done is normally with 15% CO2 in nitrogen.
Okay.
In the test to Korea, which was done on 100 kilogram scale, that was actual flue gas, but it's the same with any scrubbing. You do have some polishing, to make sure you take out all the SOx and NOx, because it's the same sort of deal with any base. You start forming stable salts. But as I said, you can't really go much below 15% with activated carbons, and clearly to get you to natural gas, 4% CO2, air capture, bores are solidly in the domain of strongly basic systems.
Sure. Just a follow-up question. Can I also know the temperature of the inlet flue gas to your system, to the adsorption column, basically?
Oh, yeah. So basically, silica-PEI is perfectly happy operating at 70 degrees. And to minimize the delta T, we're generally desorbing at 130 degrees. Obviously, activated carbons, you need to drop the temperature right down. To get 8% CO2, you need to be 25 degrees, and without polyurethane polyisocyanurate form derived carbons, we managed to get that up to 40 degrees, but clearly your regeneration temperature is a bit lower. But having said that, you're absorbing moisture, so you need to be fairly high to drive off the moisture.
Okay, thank you very much. Thank you, John.
Okay.
Is Parvis next on my?
Yes, Parvis, come on. Parvis.
Yeah, but I think the answer is the deal is exactly the same with adsorbent technology as it is with amines with respect to SOx, NOx, and any extraneous metals which might get through. Heat stable salts are pretty much a killer for amines, but for PEI, if you do absorb CO2, and we published this a long time ago, you can still desorb SO2 at temperatures below which the polyethylene imine starts to decompose. So instead of 130, 140 degrees, you're generally up to a bit over 200 degrees if you want to desorb what's essentially formed much more stable complexes than carbonates with CO2.
So that's the analog to thermal reclaiming then, just cook it. Okay. And do you need to do any neutralization of the acid gases, or do they just come off?
Yeah, well, John, it's the same sort of deal as for amine scrubbing. You clearly want to get them down to a minimum.
No, but after you when you in the reclaiming process, do you?
So yeah, we're not doing reclaiming as such, because if we absorbed a lot of CO2, we would have a separate reclaiming step where we would desorb the CO2 somewhere around about 250 degrees. With the polyethylene imine, if it got ruined beyond all control, we do know how to remove that degraded PEI to leave you the silica, and the silica then can be recycled. Okay. So, in terms of the overall picture, we're looking upon the silica as a component that can be ultimately recycled.
Yeah, that's interesting.
But yeah, okay. I can't really give you any.
No, that's interesting. Marco.
Yes.
So Marco. Yeah. This is a great question. How much potassium is retained within the carbons? So yeah, we've done a lot on this, and you probably guessed if you wash out all the potassium, you get no effect. So you just have to control your washing. But typically, you only need to leave in about 1 to 2% potassium. So you need actually very, very little. But the rub is to do effective KOH activation, you need incredibly high mass ratios of KOH to carbon, and you're not going to get anybody who's going to put in 1 ton of carbon and 2 tons of KOH into commercial facility. The best we can do, and this is due to talking to people, is you can make a normal activated steam carbon and then post-treat it with KOH, because if you do it that way, you can reduce the amount of KOH you need down to a minimum. But to do that, clearly you've essentially got 2 activation rather than one activation step. And even for the best performing material, the waste polyurethane form, even though it sounds trivial, controlling low oxidation on solid materials is challenging, to say the least.
Yeah, and regarding this, so I mean, if you have potassium, you have higher heat of adsorption for CO2. Does that also happen with water? So does your material becomes also more?
Well, the water, you just have to desorb as steam. So that's really what increases your regeneration energy. So carbons have got the advantage over PI, but the silica-PEI, if you just accept the figure I quoted, somewhere around about 2.5 gigajoules per ton of CO2, activated carbons can get you down to a bit over 1 gigajoule per ton of CO2, but that's based on not co-absorbing any water. As soon as if you only co-absorb 3-4% moisture, you're adding 1 gigajoule per ton onto your regeneration energy. So you can see your 1 quickly goes back up to 2 for activated carbons, and that's really very, very much the focus is, like what simple treatments can you do during activated carbon preparation to try and improve the selectivity of CO2 over moisture. I mean, it turns out CO2 absorbs super fast on activated carbons. You're reaching close to equilibrium capacities within a minute. But it's the design of whatever continuous system. You're talking about a minimum residence time of somewhere around about 10 minutes for your solid adsorbent, although clearly the gas residence time is only a few seconds.
Okay, thanks a lot.
Colin, could you say a little bit more about that? You said whatever contact system you've got and how quickly you can do it. I mean, what options are you considering? You mentioned fluidised-bed.
Yeah, so fluidised-bed, and this has really been the focus of the silica-PEI, because PEI is an excellent binder. So the silica-PEI has excellent mechanical properties, and the amount of degradation you get in continuous circulating silica-PEI for periods of several weeks is minimal. And the problem with carbons, I mean, you just have to look at any granulated carbon. It just doesn't have the physical strength, and that's why we got very interested in carbon bead materials. Carbon beads are expensive because you're starting with resin precursors rather than something like coconut shells, which increases the cost. But the strength is very good. The particle size deal is excellent. You can increase particle size of the probably beyond half a millimeter beyond, and still not suffer too much in terms of kinetics rate of
Fluidised-bed
CO2 absorption. But you do suffer that. Clearly, you can't use fluidised beds, and so you really have to look at some moving bed technology where your adsorbent is sinking, shall we say, slowly, goes through adsorption zone, warms up, desorption, cools down, and then goes around the cycle again. Japanese have done a bit on those systems, but they haven't really reached anything you would consider to be a serious pilot plant scale.
What about some of the rotating wheel systems?
Sorry, do you really want to bring out the grumpy old man in me again? But
oh well, maybe.
Yeah, because but the rotating wheels, everything's gone very, very quiet. And the reason why everything's gone very, very quiet with rotating wheels is desorption is a much slower process than adsorption, where you only need literally a few seconds residence time, and the rotating wheels that were proposed, certainly gave a visual impression, but it was essentially equal split between the adsorbent and desorb. And the other thing is, like, how do you heat up and cool down the stuff between the respective cycles?
Yes.
So, but I think everybody was talking about rotating wheels, I don't know, 5-6 years ago. It's all gone quiet.
Yes, well, Svanta's picked up from Inventis, different management and everything. Yeah.
Sorry, so just a short read. I can multitask and read chat at the same time. So, Angel's just asked a question. What desorption temperature?
Yeah.
For silica-PEI, and yeah, it's a compromise between time and temperature. 140 degrees generally gets CO2 off fairly quickly. Time scale 10, 15 minutes. Drop to 130 degrees. As simple rule in terms of kinetics. Drop the temperature 10 degrees. Everyone takes roughly twice as long. That's pretty much the case here. We were worried about molecular weight distribution because it's a polymer, so you've got a whole wide range of molecular masses. I mean, it turns out we started off using molecular weight of 800, and one of the things we saw in our earlier work that after the desorber, we did condense a small amount of liquid, which we took as very low molecular, and we analysed it, and it was very low molecular weight PI, which had just sort of evaporated from the desorber. So as you've got high molecular weight, just tailoring your molecular weight distribution, clearly you can avoid any significant evaporation of the polyethylene in it. I mean, a big danger is urea formation. And I guess the key question is, so clearly you've got two options. You can use steam or you can use recycled CO2. Recycled CO2, because you're desorbing essentially against 1 atmosphere of CO2, generally means you need to put the temperature by about 15 degrees. We found our best compromise is a mixture of steam and CO2. If you use 100% steam, if you're not careful, you do run the risk of defluidisation. Some agglomeration starting to occur in your bed. I mean, in terms of the economics, it doesn't really matter. It's covered in our 2017 paper. It doesn't really matter too much whether you are using CO2 or steam, but clearly those are your only options to generate a stream of pure CO2.
Yeah. I just see if anybody else has got any other question, but I just finished what I was asking. Just you're saying that moving bed reactors, you think, are the way to go
for carbon materials.
And how do you move the bed?
Well, it's, yeah,
Auger it out at the bottom or something?
yeah, it's very difficult. I mean, linked fluidised beds, certainly in my opinion, are the best option, and you know it's work for real. Sorry, I should just add that Kia operated their system on potassium carbonate, forming potassium bicarbonate, but clearly you need a lot of moisture present in the system for that to happen, and the enthalpy of dissociation is pretty high. So with that system, you're pretty much really in terms of early MEA territory in terms of your regeneration energy, something over 4 gigajoules per ton of CO2 capture, and that's why clearly Kia were interested in our system and came to us to clearly drive down regeneration energies, which we think for silica-PEI, 2.5 gigajoules per ton of CO2 is achievable.
Yeah. Okay. We've got 2 more questions. Let's take them in reverse order. So, Darren, do you want to ask your question first, and then Philip can have a good winding up question. Darren.
Hi there. Sorry. Something a layman. I just want to ask a question. Have there been any work done using activated carbon stabilizers of thin film in terms of in replacement of a mechanical bed?
Yeah, I mean, that is a possibility, and it could well be possible, but it comes, it all boils down to preparation. Costs in terms of getting the carbon into a thin film. Just to mention on a similar note, clearly you've got your carbon and you can put in various coatings to try and reduce your moisture uptake. In other words, improve your CO2 over moisture selectivity. So, I mean, we've looked at a lot of silicons, and the reason I didn't put it in the presentation was partly due to time. But yeah, silicones work, but unfortunately, CO2 absorption is also reduced. So essentially, you end up with the same CO2 to moisture selectivity.
Okay.
So I mean, it is quite ironic that, and we are looking at, just to prove it's not fluke, we are looking at coconut shells from a number of sources. To work out what it is in the surface chemistry, but is giving much lower moisture uptake compared to what we thought were our supreme new adsorbents, made from waste materials. But unfortunately, whilst we give higher CO2 uptakes, we're also giving higher moisture uptakes.
So you're looking at coconut shells from different sources. Is that what you said, Colin?
Yeah. If you want a microporous carbon, coconut shells are the most widely used precursor.
Is it how they're grown that makes the difference, or how you?
Well, you just have to look at the physical properties. So, it just means that you are you end up making relatively strong granulated material, so it's as simple as that as well. Coconut shells are used to produce microporous carbons, and that is the irony that the carbons we've looked at, those are the ones commercially available, which do give the lowest moisture uptake.
Okay, Philip, let's have the last question.
Hi there, Colin. Good to see you. Thanks for your presentation. Yeah, I just thinking back to where you started that presentation and that chart that showed all of the options that were in play best part of 20 years ago now. I'm thinking of that diagram that Jose Figueroa of US DOE used to show with all of the progression from first generation capture through to third or fourth generation capture media. And clearly, well, you said it yourself, none of those have actually become a commercial reality to this point in time. So I'd just like you to take off your solid adsorbent hat for a moment and be completely neutral. I've followed your work on solid adsorption with a lot of interest, but taking that hat off, what do you think are the best prospects in terms of either absorption or adsorption or other carbon capture processes that stand a chance of being economically attractive going forward?
Yeah, if I can slightly dodge the question and put my grumpy old man hat on briefly, one needs a common framework for comparison. Mm-hmm. And I think, the cost per CO2, per ton of CO2 captured basis, I don't know how long is everybody depreciating their capital over. What assumptions are made on energy integration, what levels of energy integration are achievable. I think I would probably defer to our honourable chair this afternoon, John, who I think can put a better perspective on advanced aiming systems. But I think Philip, what I know about advanced aimings, okay, might give you low regeneration energies, will still degrade. And what is the cost of a secondary tertiary aiming compared to the cost of MEA? So, ducking the question, and I think just really limiting the question for the purposes of this afternoon is solvent systems versus solid systems. I'd be quite interested to hear what John has to say.
That was
well,
definitely.
I think, yeah, well, maybe that wasn't the question Philip asked, I'm sure. Well, no, but I agree with the grumpy old man in this case. I think no, but you see some promises, but the evidence, and I've just come across it recently, actually, doing a post-combustion capture review. The evidence is that
I think we've lost John, but
just at the vital moment. Just at the vital moment. Carry on, John.
Yeah, sorry. The variable operation costs and boundary dam are about $30 a ton of CO2. Most of that must be solvent. And on Petra Nova, the variable operating costs are about $15 a ton, again, of which most of it must be solvent. And it's pretty obvious with those numbers. The cost of the energy costs are much lower. It's pretty obvious why with those numbers Petra Nova isn't working, because capital's not an issue. It's just operating costs. And if you can't run the plant with an oil price below $80 a barrel, which is what they said, then your operating costs have got to be pretty high. So, practical things and unexpected things do.
John, if you've got what you've just said in writing, could you send me the references, please?
Yes.
Or anybody else out there? Because I must admit, when I heard the sum $20, 20 euros for aiming replacement costs, I thought, even with reclaiming, etc., surely it can't be that much. And that's really was the sort of motivation for, I would say, developing the simple framework to keep your costs below €10, £10, $10 per ton of CO2 captured, what do you have to do in terms of lifetime against production costs for adsorbents?
But the benchmark for MEA will, the cost for that at current, basically natural gas prices, which set the MEA price because it's a commodity, it really is a few dollars per ton of CO2. You just couldn't, you close the plant down.
But natural gas separation is a lot,
you could always run a plant to chew up MEA, but you wouldn't be allowed to, You'd have to run it better than that. And those running costs would come down to $1 or $2 a ton, I think. But yeah, it's practical stuff like this that's going to get us. I mean, the other thing actually where solids could, of course, be very interesting is fugitive emissions. MEA fugitive emission, or amine fugitive emissions will cause some questions about transformation into nitrosamines and things like that. So if you can cut down the solid emission, the fugitive emissions with solids, that is an interesting feature.
Yeah, but I mean, if all you want to do is just, absorb organics from vapors, there's literally hundreds of granulated activated carbons on the market, which will do that.
That's an interesting comment. Yes, you're right. You're right. No, I don't think anybody's doing it, but people are starting to talk about a final polishing stage after an acid wash. Good point. Yeah. Yeah.
But I think, it's just taken as a given, and, going back to Philip's original question, in any comparison, it has to be exactly on the same gas before I think you can come up with any truly valid comparison. And I think, you need to, shall we say, have a very strict rule book operated, in terms of your capital costs, how long are you depreciating those over, to make sure, even in terms of, life cycle analysis, what are the CO2 emissions associated with both the costs of adsorbent and liquid amine production.
I mean, the other thing though, Colin, in reality, you have an incumbents advantage, because when it comes to making a decision about a plant, the risk-adjusted cost of capital for something that exists.
So I think, the key point is, once you've got your nice diagram, where solid adsorbents are at the minute, you need to do one hell of a lot more, somewhere around about the 10 megawatt scale, just to get the confidence to then make the next leap to, the order of a few hundred megawatts.
Yes. Yeah.
And clearly, what the reality is that solid adsorbents across the whole piece globally are nowhere near that position yet.
No. And what do you think?
Or otherwise, as you say, if people have to make a decision on a demonstration, they're going to plumb for advanced amine plant every time, because until you get to that crucial threshold of really having the confidence to make that big leap, based on what you've done successfully at somewhere around about the 10 megawatt scale, unfortunately, you're not going to change that situation.
Yes.
I must say that's my gut feel as well, that is the area that will probably have the best prospects going forward, unless something else comes along to displace both absorption and adsorption. Things like anti-sublimation, which didn't go anywhere when Alstom looked at that in the past.
Yeah. Oh well.
Great, thanks for that. Interesting debate.
Hang around for another 20 years to see the result, eh? See how it pans out. Be good. Okay, thank you very much, Colin, for that grumpy old man's view of solids capture. You can do it again. Vic, are you still there? Do you have anything you want to announce, or other than come back next week?
Hello, yes. I'd just like to say thank you to Colin for sharing his expertise with us today. It's always good to see lots of questions.
Yeah, it's been great. And this is the first time since lockdown I've actually talked for over 25 minutes. So my voice is beginning to go.
Okay, well, whether that's a good thing or a bad thing, thank you very much. Yeah, I'd just like to say, in terms of next week, we do have another guest lecture, this time again, 3 o'clock. Next week, we've got the politics of energy, how politics shapes the energy transition. And that's with Dom Goggins from Praseg. So hopefully we'll see some of you on the lecture next week. But once again, thank you very much, Colin, for joining us. It was very informative.
Yeah, it's been great. Thanks.
Thank you.
Thanks, Colin.
Yeah, cheers. Yeah, bye.
Thank you very much, everybody. Bye.